this video series, we'll be looking at isotopes and relative atomic mass. Now, isotopy is just a phenomenon whereby atoms of an element exhibit different mass numbers but have the same atomic number. Okay, isotopes are just the atoms of the same element that have different number of neutrons. So what you see that is changing is the number of neutrons. If you consider this example of chlorine isotopes, okay, we have chlorine of mass 35, which is the atomic mass number. This is the atomic mass number. This is the atomic mass number 35, and we have chlorine of atomic mass number of mass units of 37. All right, so now this particular one is the atomic number. This is the atomic number, okay, and this is the atomic number. Like I said, we have the same atomic number, but the mass number, keep changing. That's what varies. That's what we have in the two isotopes. And because the mass number changes, varies, we are going to have different neutrons. This one gives you 18 neutrons, this one gives you 20 neutrons. Now, the atomic mass number, which is atomic mass unit, right, is the number of protons plus the number of neutrons. Okay, the number of protons plus the number of neutrons. The atomic number is the same thing as the number of protons. Okay, the atomic number is the same as the number of protons. So if we have the number of protons for the isotope of chlorine of mass 35, we have the number of protons to be 17, right? And the mass number, which is the atomic mass number, okay, is 35. So we're going to have neutron. Our neutron will be mass number minus the number of proton, because number of proton plus number of neutron gives you the mass number, right? So just subtract this. This 35 minus 17 will give you 18. That's the number of neutrons. Then we have 20 minus 17 is going to 27 minus 17 rather is going to give you 20 neutrons. All right. So now we can have the abundance. The abundance just means the amount of this particular chlorine of mass 35 that we have in the isotope. So we have 75% of chlorine in the isotope. That's the isotope of mass chlorine of mass 35 has 75% abundance. Then we have chlorine of mass 37 that has 25% abundance. That means we have more of chlorine of mass 35 than chlorine of mass 37. Now, the relative atomic mass of an element is the average value of the isotopes of the element. It takes an account the percentage abundance of the isotopes. I'm still going to discuss that in the next slide. Now, for you to calculate the relative atomic mass, which can also be the weighted average, or the atomic weight. So, for you to calculate the relative atomic mass, you look at the abundance of each isotope. For this particular one, isotope of mass 35, it has abundance of 75%. Okay, you multiply it by the mass. Okay, that's the mass 5 plus 25%, which is of the mass 37. That's the abundance. That's 25 multiplied by 37 is going to give you the relative atomic mass, or we call this a weighted average. Now, let us look at the following examples to explain the atomic mass the more. Let's say we have two Sienna cars, right? Two Sienna cars. I want to consider isotope. Isotope is like having two models of a car. For example, let's say this is a Sienna car, and we have this model as model GX, and this one as model GE. Now let's assume that this particular one weighs 4,000 kilogram. That's 5 seats. Probably you can say that this one has a cloth leather. Okay. Then we have uh, uh, sorry, a cloth seat. Let's say this one have a cloth seat. Okay. Let's say it have a cloth seat. Then we have this one. Maybe this one have a maybe a leather seat. All right. Okay. Okay. You will discover that this particular one, it doesn't change the fact that we have these two cars as Siennas. So we have this GX model that has different weights, but have 5 seats. This one have TV. This one just have a radio and all that. So we have this just like a isotopes of chlorine. This one is chlorine mass 35, and this one is chlorine of mass 37, like the one that we discussed the other time. So despite that of the content of what they have, okay, they still remain Sienna cars. All right. Now, if we were to calculate the normal average of the weight of these cars, not taking account of the amount that they have, the amount that they have. So let me just clear this one out. So we're not taking into consideration the amounts or the abundance of what the abundance of the type of Sienna cars that we have in the system. Now, let's say that we are to calculate the weighted average, I mean the average of this. Normal average, you will say, if you want to calculate the normal weight, uh, average weight of these two cars, we just do this 4,000 kilogram, which is this, then plus this 5,000, okay, kilogram. So this one will give you, that's divided by 2, that's the average, that's be 9,000, okay, divided by 2, you're going to have a 4,500 kilogram. All right, that's the average I want to have. But the weighted average is different from this. The weighted average is different from this because we need to consider the amount of these particular cars that we have, the amounts that we have. Now, if we were to consider the numbers, that's the average, the amount of this particular Sienna that we have in circulation. Probably we're a production company, we produce 95% of this because of the demand from people. They prefer using this kind of Sienna cars than this. So we have the 95% of this, in abundance. We have 95% of this in the system, while we have, just 5% of this in the system. So you can see that, okay, when you try to count the number of cars probably in Lagos, you have 95% of Sienna GX, which is this. No, if we were to find the weighted average, which looks more like the atomic marks, the weighted average of the Sienna, taking into consideration the amount of each model, that's the weighted average, considering the amount of each model. So we know that we have this at 95%, we have this one at 5%. Don't forget it's 4,000 kg. So I'm going to take this maths, that is 4,000 of this particular one, then multiply by the abundance, that is the amount of the Sienna cars that we have in the system, and I'm going to convert into decimal to do 0.95. Okay, so this for the Sienna GX. Okay, then I'm going to add it to, okay, this particular one is 5,000. That's 5,000 kg. That's the weight. Then multiply by the amount that we have. That is 0. I'm going to convert it to decimal. That's 0.05. Okay. This particular one, okay, is the model GE. Okay. So now, if you do this calculation, I'm going to have about 4,050 kg. You do the calculation of here. Now, what does that one mean? Which is different from the previous average that we have, which is about 4,500. Right now, this is a weighted average. This is a weighted average of the two weights. This is the weighted average of the two weights because, and you discover that this is 4,050 kg is very, very close to this particular one of 4,000 kg. Why? Because we have more of this sienna in circulation. We have more of this sienna in circulation. We have more of this sienna in circulation than the sienna of G. So we just have 5% of this. So the weighted average is very close to this particular weight because we have more of it in circulation. Now having seen this, let's now use that to solve certain problem in atomic mass. All right, so just like the sienna, the copper has the atomic number 29, and we have the atomic mass of 63, atomic mass unit of 63.55. Now, just like the cars, we have GX and GE. The copper also has different isotope. We have copper 63 and copper 65. But you discover that the protons are the same, okay, which is the atomic number. It doesn't change. We only have the neutron changing, okay, because of difference of atomic mass number. Now, we are given the atomic mass unit of 63, atomic mass unit of 65. All right, in how many abundance? We have this one at 69% abundance, and we have this one is 31% abundance. So what do? I will take this particular 63, then multiply by the abundance, which is 0.69, then plus this particular one, that's atomic mass unit of 65 that we're given, multiply by this particular one, which is 0.31%. So if you do that, you're going to get 63.62. Now, what does this imply? It means that we have the weighted average, okay, weighted average or relative atomic mass, okay, you can also call it weighted atomic weight, relative atomic mass or weighted average to be 63.62. Now, this answer, 3.62, is very, very, very close to this particular one, to this particular copper, okay, very close to this. Why? Because we have the copper 63, we have the abundance 69%, which is more than the abundance of copper 65, which is 31%. All right, so just a quick recap before we have some questions to solve. Now, the atomic mass, which is the weighted average of all elements of the isotopes based on their natural abundance, is very, very simple to calculate. So what are the two steps that we need to know based on what I've said? You multiply each isotope's mass by its abundance. Multiply the mass by the abundance. So you can convert the abundance, so you can multiply in percentage, or you can multiply in decimal. If it's in percentage, you finally divide your answer by 100. Okay, so when you add this value together, you have the value of the two isotopes, probably the isotope of chlorine, maybe 35, and chlorine 37. Once you add it together, it's going to give you the total atomic mass, or we call it atomic weight of the element, or the relative atomic mass. Now, let us look at different examples. All right, so you are given the sample of containing 98% of carbon 12, and we have 2% of carbon 13. These are the abundance, 98%, and this one is 2%. So first, you can convert the percentage to decimal. So we have a sample of 98% becomes 0.98 of carbon, and we have this one converted to decimal, going to give you 0.02 carbon 13. So we need to multiply the percentage abundance with the mass of the carbon that we're given. So we have the mass of carbon, that's 12, and carbon 13. So 0.98, which is the abundance of carbon 12 multiplied by carbon multiplied by the 0.98, which is the abundance of carbon 12 multiplied by the 12, which is the mass, will give you 11.6. Then you have 0.02 multiplied by 13, which is the mass of 13 with the abundance. So if you add it together, it's going to give you the weighted average, which is the atomic mass, or the relative atomic mass. All right, so let us look at this particular example. There are two stable isotopes of chlorine, that's chlorine 35, which weighs 34.97, that's atomic mass units. We have chlorine 37, which weighs this, right? And if the relative atomic mass of chlorine is 35.45 AMU, what is the abundance of each isotope? Don't forget that the abundance of each, the relative atomic mass, mass is equal to the abundance, okay, multiplied by the abundance multiplied by the mass, okay, the abundance of one multiplied by the, and abundance of the second multiplied by the mass of the second that you are given. Now, for every abundance, for example, if you have a chlorine, if the abundance of one is 35%, definitely the abundance of the second one will be 65%. Okay, so the second one will be 65%, which makes 100%. All right, so if the abundance of this one converted to decimal is 0.35, then this other one would be 0.65, okay, which make it one whole number if you add everything together. Now, because we have we're not given the abundance, and that's what we want to find. So if you represent the abundance of one, okay, we say that let the abundance, okay, of isotope, okay, chlorine 35 to be maybe X%. Okay, so then for the abundance of chlorine 37 will be 100 minus X%. Okay, we can also do this one as if it's X, then the second one can be 1 minus X. That is if you convert it to decimal. All right, so I'm going to use the decimal one to do my calculation. Okay, so if the abundance of the chlorine, if the abundance of the chlorine 35 is X, then the abundance of chlorine 37 will be 1 minus X. All right, so and I have the weight, the average mass units, the atomic mass units to be 34.97 for chlorine 35. So for chlorine 35, okay, all right, I have the atomic mass unit to be 34, okay, 0.97, then multiplied by X, which is the abundance, then plus the chlorine 37, okay, I have the weight, that is the atomic mass unit, that's 36, okay, 0.97 multiplied by, okay, this is the abundance, which is 1 minus X, then is equal to the relative atomic mass that we're given is this. Everything is 35.45. All right, so this one will give me 34.97x. All right, so then that's plus 36.97 multiplied by 1 minus x, which is this. All right, so that's 4.97x plus 36.97 minus 36, okay, that's 0.97 multiplied by 1, that's minus 7.97x this. So if you do your calculation, you're going to have minus 2x minus 1.52, you're going to have 0.76, okay, which is x, okay. Then that's 0.7, which x give you like that 76% abundance of the chlorine of 35. Okay, so if you calculate this one, 1 minus x, which will be 1 minus if you look at it, if this is 76%, then definitely this one will be 24%, okay, because that is 1 minus 0.76 would actually give you 0.24, okay, which is 24% of this particular isotope. So this one contains 76% abundance, and this one contains 24% abundance. All right, so gallium has two stable isotopes, and the mass of gallium 69, that's 60.11% abundance, which is the abundance of the isotope of gallium 69, and we have gallium 71. We have 39.89% abundance. Okay, the atomic mass units, they are for 69 is this, and for 71 is this. So this is atomic mass for 69, mass 69 is atomic mass of mass 71. So calculate the relative atomic mass. So we have the gallium, okay, gallium 69 has AMU, that's atomic mass unit of 68, okay, 0.926, and have the abundance of 60.11%, while we have the gallium 71 has AMU, atomic mass unit of 70.925, and we have all right, so we have the AMU, like I said, to be 70.925 for gallium 9, and we have the abundance, that's the abundance to be 39.89%. All right, for us to calculate the average atomic mass of the gallium, so we'll take the one of this particular one, that's gallium 69. So we have the AMU, that's atomic mass unit given at 68.96. So we'll take that 68.926 multiplied by this, convert this into decimal, that will give you 0.6011. Okay, then plus we have this one is 70, atomic mass unit given 925 multiplied by, convert this to decimal, that's 0.3989. okay, so if you do this calculation, it's going to give you, all right, so we're going to give you 69.72, that's 41.243 plus 28.29, going to give you 69.72, and you discover that this particular one, which is 69.72, is very close to this atomic mass. This is the relative atomic mass, or the atomic average atomic mass, average atomic mass, or the weighted average, or the relative atomic mass, or atomic weight. Depends on the language. It can be called those names. Now, you discover that 69.72 is very close to this particular one, which is the mass of the gallic 69. Why? Because we have 60.11 abundance of gallium 69 than we have more abundance than gallium 71, which has 39.89%. All right, so let us look at this. We have two isotopes of chlorine with mass numbers of 35 and 7 respectively. If the isotope exists in ratio 3:1, okay, so we have the two chlorine, okay, chlorine 35, and we have chlorine 37. Okay, so they exist in ratio 3:1. Okay, the lighter isotope being more abundant, what is the relative atomic mass of the chlorine? So we have to find the relative atomic mass. Okay, so if we want to find the abundance of this, so we know that this exists in 3:1. So that means the total ratio, that's 3 plus 1, which is going to give you 4. So you want to calculate the abundance of this to be as if you're doing in percentage 3 over 4, this 3 over 4, which is the total, multiplied by 100%. So if you do that, this is 25. Okay, this is going to give you 75% abundance. So that means you're going to have 75% of abundance of this. Okay, and if we already have 75% abundance of this, then subtract from 100, it's going to give you, this is going to give you 25% abundance. So that's how to get that one done. So now that you've known the abundance, then we just find our relative atomic mass. And its atomic mass is this. We're going to give the mass of this, mass 35, okay, multiplied by this particular abundance, which is 0.75, okay, then plus 25%, that's 37, which is the mass, multiplied by 0.25, which is the abundance. So once you do this calculation, it's going to give you, it's going to give you 35.5. So that is the relative atomic mass of chlorine. All right, now the relative atomic mass of chlorine that we've just gotten here, okay, is 35.5, is very close to the mass of 35 that we're given. And you would see the reason being that we have chlorine of 35, which is more in abundance than chlorine of 37, of mass 37. All right. Now, in this particular one, we're given the relative atomic mass of an element is 21.5. That's the relative atomic mass. And the two isotopes are this, 20x. So this, don't forget, this is the atomic number, and this is the mass, relative atomic mass. Okay. All right. This atomic number is also the number of protons. Okay. So we have to calculate x, which is the atomic mass of this particular x. So we are given two isotopes of 2010 and this other one x10. Okay, so and we have that this particular one is 25% in nature, that is the abundance, and we have this one as 75% in nature. We have to calculate x. So the relative atomic mass 21.5 is equal to, don't forget, this mass that we're given is 20. So we have 20 multiplied by the percentage of this, which is the abundance, which is 0.25 plus. Then this particular one, we don't know this, which is the one that we're looking at, this is the x. Then multiply by this particular one, which is 0.75. All right, so once we do that, do the calculation, we're going to have, so our answer will be 21, that's 21.5. You know, this one is 5 plus 0.75x. So you're going to get your x to be 22. Okay, if we do the calculation, it's going to be 22. That means the two isotopes that we have is 20, 10x, and we have 22, x 10. So those are the two isotopes that we have. All right, so with this, we've come to the end of our topic on isotopes, atomic mass calculation, and how to calculate the abundance of any isotope once you are given the mass in any of the calculations. All right, so don't forget to subscribe to our YouTube channel. Tell your friends about this. Like the video, and we'll see you the next week. I hope this has been very informative. Bye.